All right, so this is number 8 on the McGehee worksheet. So we have an amusement park ride given here in this diagram. The riders board this pod at point A. They're lifted vertically at a constant speed. This is actually important right here. See, it says constant speed from A up to B. The pod is then moved horizontally from B to C and is released at point C. Between C and D, the pod is in free fall, which means the only force acting is gravity, no friction. The pod then follows the circular path between D and E. Now look, here's the significance of this. The radius of this circular path is right there, right? What would this distance here be? Would that be the radius or no? That's also the radius. So we're going to be using this to figure out the vertical drop. When we get to part B here, we're going to need the vertical drop from there to there, right? The H. Now what's that H going to be? It's going to be the distance from C to D, which we have right here. And then what are we going to add to that? We're going to add the radius, right? Because this would be the radius of that circular path to get the total height H. Okay, so then it says the brakes are applied after point E, bringing the pod to rest at point F. Okay, so in here, from point E to point F, this is the only region that has friction. Everything else is frictionless. Okay? Now, so we have all this data, we got times, we got the mass of the pod. I'm going to erase these questions so I have room to solve this. So you should have the worksheet in front of you. Okay, first question. What is the power supplied by the model motor lifting the pod between A and B? So we're looking for the power of the motor that lifts the pod from here to here. So what's the basic definition for power? Well, okay, so we're on part A. Power, you could say power is energy per time, or you could say power is work per time. I'll solve it both ways. You could look at it either way, but either way it comes out as joules per second. So if you looked at this as energy per time, what type of energy is the pod gaining as it goes from point A to point B? What type of energy is the pod gaining? Is it gaining kinetic? No, because remember they told us in the problem right here, the pod is lifted with constant speed. If something moves with constant speed, it's not gaining kinetic. So what type of energy is the pod gaining from A to B? Potential of gravity, okay, over time. So potential of gravity is MGH. Okay, so you plug in. The mass of the pod is 0.5 kilograms. Gravity, McGehee's using 10 for this whole worksheet. And then H is from A to B. That's right here. From A to B is 2 meters. Okay, and then the time is right here. That's 5 seconds. So this comes out as 2 joules per second. What's a joule per second? A watt. So this is 2 watts. Now look, check it out. If you would have looked at it as work per time, well, let's just look at this pod. So here's the pod being lifted. I'm going to go over here. Here's the pod being lifted. What are the forces on the pod? You got mg down, and then you got the force of the motor, right? The force of the motor lifting the pod. If it's being lifted at constant speed, which it is right here, if it's being lifted at a constant speed, what has to be true about those two forces? They have to be equal, right? Because if the force of the motor was bigger, it'd be accelerating. All right, so what's the basic definition for work? Work is what? Force times displacement, okay? So what's the force of the motor? What did we just figure out? The force of the motor is equal to what? mg, and then what's the delta x here? It's h. So look, we get the exact same thing. mgh over t. Okay? All right, that's part A. Let's go to part B. Okay, so part B, what is the speed of the pod when it reaches point E? Okay, so the pod starts here at point C, right? It gets moved over and then it's released. Now, how are we going to find the velocity of the pod when it reaches point E right here? So look, what type of energy does the pod start with up here? It starts with potential of gravity. Now, whenever you use potential of gravity, you have to have a 0 point. Where's your 0 point going to be? Are you going to stick your 0 point down here? Where should the 0 point be? At the lowest point in the problem, which is right here. Right? That's the lowest point in the problem. Now, we got to figure out what h is. What's that total h? Well, we have to add two distances, c to d, and then the radius, because the radius is that right there. Everybody see that? C to D, and then the radius. So this is going to be 1.75 meters. Now, what type of energy does the pod have at point E? It's going to be all kinetic. Was there friction in between? Nope. So what does that tell us? Potential of gravity is equal to that kinetic. So here's how you do part B. The potential of gravity initial at point C is going to be equal to the kinetic final at point E. Okay, so you go mgh equals 1/2 mv squared. The mass cancels. We don't even need the mass. And then v is going to be square root 2gh. 2 times 10 times 1.75. So this gives a velocity of 5.92 meter per second. Okay, third question. What is the net work? Okay, look, whenever you see net work, there's a really cool equation. Who knows it? What's work net equal to? Change in kinetic, always. The total work done is equal to change of kinetic. So let's just go ahead and do that. So we're looking for, so we're on part C. Part C says, what is the net work from E to F? All right, so work net is equal to change of kinetic, which is going to be kinetic final minus kinetic initial. So over here is the final. Point F is the final. Point E is the initial. What's kinetic final going to be right here? 0. Kinetic final is 0. So that means that the work total from point E to point F is negative kinetic initial. Now, why does it make sense that the answer comes out negative? Because what do we know about the net work in this area here? Is the net work in the direction of motion or against the motion? Against, so it makes sense that it's negative. And so it's going to be negative 1/2 mv initial squared. So that's going to be negative 1/2 0.5, and then this was 5.92 squared. And so this comes out as negative 8.75 joules. Now, is that the only way you could have done this? But you know what? The bell's almost going to ring, so I'm going to leave. You also could have figured this out from the big, long, kinetic initial plus potential initial plus work done equals kinetic final, right, plus potential final. You could have figured it out from that. All right, but hold on. Let's keep going. Don't pack up yet. Okay, D. What is the magnitude of the average friction force acting on the pod from E to F? So we're looking for the frictional force from E to F. Now, you could do this by summing forces, free body diagram, sum the forces. You'd have to use a kinematic. You could figure this out back when we were doing forces. But how would you do this using work and energy? Well, look, from E to F, here's what we know. We know that the net work is negative 8.75 joules. Guys, what was the only force that did work from E to F? The only force that did work was what? Friction. So the work net is equal to the work of friction, right? The only force that did work was the work of friction. So you go like this. The work of friction must be equal to negative 8.75 joules. Well, what can we say about the work of friction? Well, what's the basic equation for work? Force times displacement. So that's equal to negative 8.75 joules. So friction must be equal to negative 8.75 joules divided by the displacement, which is what? From E to F, it's 1.25 meters. So the frictional force must be -7. Oh, but it says magnitude, right? The question says magnitude, so I guess you could just leave off the negative. Just leave the negative off. The negative's the direction. All right, then, last question. Oh my goodness, this is like the longest one. The last question, what is the rate? Ooh, you know what, let me leave this for a second. Dude, what are they talking about here? The rate at which kinetic energy is converted to heat. Guys, what is rate? Rate is anything per time. So this question is asking for energy per time. Rate that the energy is converted to heat. So what are they really asking for here? The power. Basically, it's joules per second. So this is question E. So the rate at which kinetic energy is converted to heat. So how much energy was converted to heat here? 8.75 joules, right? So we have 8.75 joules of energy being converted to heat in how much time? In 1.25 seconds. So this comes out as 7 joules per second, which is 7 watts. So like, look, this is 7 joules of kinetic energy converted to heat per second. 7 watts.